Okay, so welcome back to another video. So today we have a functional equation that we would like to solve, and that is to find a function that's differentiable continuous of f of x such that it satisfies the following. So we have f of x plus y is equal to f of x times f of y subtract with 1 minus f of x times 1 minus f of y. And then that's it, also with the condition imposed that f prime of 0 is equal to some arbitrary constant. We'll call this alpha. So functional equations are generally easy to solve if you know the techniques. You want to find some initial condition for a function itself when some value. So in this case, an easier way to find such values that you just plug the trivial inputs x, y, both of them equal 0, plug that in, and of course that is the first step obviously that we want to show first before getting on to the bigger picture. But what makes this problem interesting is that eventually, as you continue to break down the methods and computation of the given functional equation we would like to solve, it actually comes down to a formula that everybody in calculus knows. And that's actually interesting to say that, since again, with this whole breakdown, it just comes to that one formula that we always use in our everyday lives and in the world of mathematics, I should also add. So that's just really the technique on how we're doing this. Just break it down. First put in your trivial case for x equals 0, y equals 0. Utilize that. Then solve the functional equation in a way that's easier to work around with. And eventually it will come to that formula. And we will eventually find what our f of x function is that satisfies this given with this condition as well. So nothing to add. So we'll just jump ahead in. So suppose we're going to let x and y equals 0. So we want to find some f of 0 value that we want to plug in for some function f, as we want to build another initial condition to use later. So if we do this, so that means I'll just plug everything over here. So that means we have f of 0 plus 0. And then set this equal to, so f of 0, so it's f of 0 times f of 0, so I'll just put this as f of 0 square. And then right here we have subtract 1 minus f of 0 and then times 1 minus f of 0 again. So I'll put it this way, so 1 minus f of 0 quantity square. That would mean that you can actually use the FOIL method to expand this out further. So now we would have f of 0, that's square. Then, so if I just distribute the negatives into everything with the expansion, so we would have -1, and then add this with 2 times f of 0, and then subtract with f of 0 square. But you'll notice that two of the terms cancel each other out, namely the f of 0 squares. So now we're just left with the, and it's also worth noting that f of 0 plus 0 is still just f of 0 itself. So now, so far we would have just, so I'll just rewrite this way. So 2 times f of 0 and then subtract 1. And so if you do a little bit of algebra, that's not that difficult to show that we can just subtract an f of 0 to both sides and then add a 1 to the other side. And so therefore we say that we've built our little initial condition with the value that f of 0 is indeed just equal to 1. So that's 1. f0 equal to 1, so we'll utilize this condition to help solve the rest from here. Let's go back into our functional equation right over here. The next thing to do is let's do a little bit of the expansion. So going back, so we have, write this as, again, f of x plus y, then this is equal to f of x times f of y. Then if we just expand this out by using, the FOIL method, so this time we would see that we just, so let's see if I can just put this as the expansion. So we would have 1, then subtract f of x, subtract f of y, and then add this with f of x times f of y. Now we notice that we just distribute the negatives into everything. So obviously you'll see that yet two terms cancel each other out. So the f of x plus f of x times f of y, and then over here they cancel each other out with the distribution of the negative. So therefore, continuing forward, we would have that f of x plus y is simply just, so everything is positive, well, except the -1, so I can just use the commutativity. So I'll write it like this. I'll put this as f of x plus f of y, and then subtract 1. We don't really have to do this substitution. That's the next step, really. But because I'm doing it this way, because it's a this will help generalize, like, well, not necessarily generalize, but this will show like the formula that everybody knows that's being implemented here. So if we say we're gonna let y equals h, right? So now if everything we plug in here. So now let's move on to the next color. So I'll put this in brown. So now next we would have just f of x plus h. Then it's just equal to f of x. Then plus f of h, and then subtract 1. Do a little bit of algebra. What I can do is I'll subtract the f of x to both sides. So this will be f of x plus h, subtract f of x. So that's equal to f of h, then subtract 1. Then what I can do to both sides is I'll just divide in h. So now this is divided by h over here, and then on the right hand side as well. And what you'll notice is that what I can do from here is that if we just use the condition that f of 0 is equal to 1, so we can make the substitution say that for f of 0, so x is equal to 0 over here, then I can actually rewrite this a little bit differently. So I'll put this equal to the right side. So we can actually write this as f of 0 plus h, then subtract f of 0, and then divide it by h. And what you'll notice is that next what I'm going to do is I'm going to take the limit of both sides as h approaches 0. But what does that involve? This actually means that this is actually forming the definition of a derivative. So in other words, if I take the limit as h approaches 0 from here, we just form ourselves the definition of a derivative. In other words, we have formed our f prime of x. Then here, the limit h approaches 0 of f of x plus h, subtract f of x, then divided by h. Then we take the limit as to both sides, so the limit as h approaches 0 of f of 0 plus h, subtract f of 0. So I'm just simply rewriting the same thing, just taking the limit. So now we just formed that this is the derivative f at f evaluated at x evaluated at 0, so f prime of 0. But we have that condition that's saying f prime of 0 is actually just equal to alpha. So now we actually just formed ourselves a little differential equation. So what does that mean? What we can do is to go back to find our f of x. Then we could just take the derivative, or the integral of both sides, the indefinite integral. So that means f of x simply just equal to the indefinite integral of f prime of x dx. So we just take this equal to the indefinite integral. So that means this is the integral of alpha dx, which is just simply just alpha times x, and then add this with c. You utilize that f of 0 is equal to 1, so we could just plug this back in. So let's see, f of 0, then that's just equal to alpha times 1 plus c, and I'll just put that this is equal to 1. That's just what we found. So obviously this is supposed to be a 0 over here. Sorry about that, 0. So obviously we know that 0 times alpha is 0, so we know that c, the constant c, is just equal to 1, and basically we are done. So we have just found our f of x function satisfying the functional equation. So therefore f of x is simply just equal to alpha times x. Now alpha looks funny, so let me fix that again. Alpha times x and then plus 1, like so. And there we have it. Box in the orange. And you could simply check to see that if you actually just plug your f of x back into the functional equation, and if it matches, then that's how you know you found the correct function, just like that. So yeah, everything here. So we just actually get to the steps. We have found, the definition of a derivative, like so. Maybe I'll underline it just so you see where I'm showing. And so there we have it. Just use a little bit of calculus and just form that differential equation. That's how we get to this step, and just like that. So yeah, that's pretty cool if you ask me.